Good afternoon again, everybody. It's almost over. I'm back. Hooray. Yeah. Let's talk about SIMD for a while, shall we? Before I start, I want to make two small apologies. One is that I wanted to launch this talk with a nice beta of std.simd that everyone could check out. I will be getting straight back onto that when I get back, and hopefully you can all try out some of the stuff that I talk about. And in addition, I wanted to do a nice case study that I could follow through this talk, but life got in the way, and here it is. So, for those that may not know, what is SIMD? Well, obviously, SIMD, or the Scottish Index of Multiple Deprivation, according to Google. Perhaps rather single instruction, multiple data. Yes, is a technology present in many modern CPU architectures, which offers parallel operations on short arrays of data. Awesome. So, in practice, we have a big loop like this, let's say. What SIMD offers is the possibility to do something much more like this, effectively unrolling a sequential loop, and these four operations will be performed in parallel, simultaneous, by a single instruction. That's great. Nothing is ever so simple. So it's important to note that making use of SIMD hardware is certainly a low-level optimization. It best applies to tight loops. If you're really worrying about it, then you only need to concern yourself with it in the hottest of your code. But I think with D, we can present some nice systems that allow us to use SIMD all over the shop without inconveniencing our code in any particular way. SIMD may improve your performance in a few important ways. One, it may reduce the number of instructions issued significantly in that it can perform 4 times or more the amount of work in a single instruction. It may reduce loop iterations significantly by a factor of 4 or more. It will increase your data bandwidth and should reduce your overall program code size, which may give you big iCache improvements as well. And often offers specialized instructions to perform lots of complex tasks, which can be useful in very sort of application-specific code. So, how do we use it? Usually, you access SIMD via a set of specific registers that the hardware offers and a set of instructions that operate on those registers. The registers look a lot like this. They're usually a fixed size, like 16 bytes is typical, but they can also be 8 or 32 or more, depending on the architecture. It's not very well standardized, but let's go with 16. It's the most common. These registers are effectively short array registers. They're never considered like a single 128-bit int, at least not that I've seen. And they can usually be reinterpreted in a whole bunch of different ways. For instance, 4 ints or floats, or a pair of doubles, or 16 bytes, and unsigned variants too, of course. So in D, we access this hardware, or at least the registers, via this __ vector intrinsic, which has recently been added. We import core.simd, and then we can declare an __ vector along with a short array declaration, which is of the appropriate length to fit the size of the register we're targeting. In this case, 16 bytes, 4 floats. So core.simd also provides a bunch of helpful aliases. For instance, this double2 int4, which make your code look a whole lot nicer. Really good. It is, of course, important to notice that these are intrinsic types. They map directly to the hardware available. DMD, at least, and ideally the D spec, I think, will not try to emulate types that aren't available on the architecture that you're targeting. There is a caveat. LDC and GDC will currently both emulate unavailable SIMD types, and the performance will probably not suffer, but you won't see an improvement. Yeah?
I think it's a very important point why DMD doesn't emulate them. Can you go over that, please?
I'll get there. That's coming. But anyway, yes, in D's sake, let's assume that they're intrinsic types and you shouldn't use the ones that aren't supported by your target architecture. And yeah, for instance, a type and width pair, which I just said that. All right. I haven't practiced this talk. Maybe I didn't go over it. Okay, so what was your question again? Why I shouldn't do it? Why did we
My
make
question
that
is
choice?
why we don't emulate
Yeah,
types.
well, this is for a performance reason. I think what D wanted to offer in terms of SIMD in the language itself was sort of direct access to the hardware for those that are interested in maximum possible performance. What I expect we'll do is produce some sort of libraries higher level, which will fill in all the gaps and give the best available options. But the hardware support, or the D core language support, should be for the most aggressive direct access to the hardware. So the standard set of operators are available. They can be used with all the SIMD types that are supported. For instance, here we can create a float 4, initialize it to a short array literal. Then we can add them together. And operations are performed element-wise on SIMD registers. In this way, they work basically like regular D array operations. So applying SIMD to a previous little example here, which we just iterate over 100 things and add some to them. If we apply SIMD logic, we can declare an array of int 4s instead, which is instead of 100 elements, it's 100 elements divided by 4 long. And since SIMD needs to operate on other SIMD types, we need to declare a variable containing 4 tens. And then we can iterate over only 25 times instead of 100 times, adding 4 tens to each 4 at a time. So now we only have 25 iterations, and this improves bandwidth since it can work on 16 bytes worth of data, 16 bytes of data at a time rather than just the 4 for an int. So that's good. So in this way, yeah, you can almost always use SIMD to significantly accelerate sort of iterative tasks. That is like a scalar workload being processed in a loop this way. But there is another popular use, possibly more popular, and that is to consider the elements of SIMD registers as components of a 4D vector. And this is really popular in linear algebra, and I think SIMD is very, very often applied to linear algebra problems. It is in fact popular in fields such as image processing, geometry processing and rendering, simulation physics, often sound and other things too. So you can do 3D audio transformations with similar algorithms. But most of my examples will consider linear algebra because most of those problems are more interesting. So we understand it basic technically. To make good efficient use of the hardware, we need to understand some restrictions and limitations of the hardware. And this is a question that constantly comes up. Why do we require this underscore vector intrinsic at all? Why don't we just optimistically, or opportunistically rather, apply SIMD optimizations to small array operations in D, let's say? And the answer is that the SIMD hardware is nowhere near as flexible as a regular D array, and the underscore vector intrinsic enforces all the rules associated with the hardware and reserves the right to produce compile errors for unsupported types and operations. It's also important to note that the limitations I will describe are completely non-uniform across different architectures. So what I will try to do is describe a set of best practices that can be applied that should give good performance on as many architectures as possible, and certainly won't hinder any particular architecture. And with a goal of maximum portability, which is important to me and many others. So the first one, this isn't really a best practice as such, but it's a requirement. You need to test your code on every target architecture. The typical approach here is to provide fallback code that will be used in lieu of actual tested support. So if you can't build and run your code on a particular target machine, you probably shouldn't run your SIMD routine, even if it might compile. Instead, use the D code until you can test it. You will probably have problems otherwise. There has been discussions about this portable SIMD library that I just alluded to, but they're ongoing. We'll get there once this is settled, I think. Second important point is SIMD vectors are always aligned. Some architectures say that it can handle dealing with unaligned vectors, but it's usually a lie. It's microcoded and it's slow anyway, so you should probably avoid it. The underscore vector intrinsic will enforce the alignment of the vectors, so all SIMD values that you handle will be aligned to the size of their their type. And you need to take special care when laying out structures and memory. Otherwise, you'll find wasteful padding all over the shop. Let's look at an example. So we've got a dude here. He's got health and a position and velocity, and this looks pretty benign, really. One might imagine this is, 4 plus 16 plus 4 is 24 bytes. But it's internally rewritten like this, of course. Turns out it's actually 4 plus 12 plus 16 plus 4 plus the gotcha on the end, another 12 bytes, in order to align the entire structure size so that you can create an array of the things. Otherwise, you'd never be able to. That's an awful lot bigger than we expected. And we can improve this situation simply by reordering our structure. So if we put the SIMD item first and followed by non-SIMD items, you, without having to really manually fiddle with your structures, you'll know it packs well. So a good rule of thumb that I like to apply is put vectors at the top. And of course, if you're dealing with classes which have virtual pointers and stuff, it gets hairy. Now the problem here is that there's still 8 bytes of padding on the end. That's a shame, and there's absolutely nothing we can do about that. So the approach is to use it. Do something with it. Use free 8 bytes, hooray. So I like to put some sort of cached data if I've got nothing else in that space. Maybe I can make use of it. Or if the padding is close to another word, then maybe you can pack down some ints into shorts or something like this.
Couldn't the layout be automated?
Well, the question was, could the layout be automated? I would say that's a bad idea. Sorry?
Is there a microphone?
There's a mic.
I'm not sure how well it works, but we actually do have a standard .typecons.align arrange for size or something. I forget exactly what it's called, but it's designed to reorder the fields of structs to make them have the minimum size once you take into account alignment overhead.
Okay.
Right.
Well, that could be very useful.
I think the general program is knapsack, right? So it's MP complete or whatever, right? But what is not knapsack because you get to fit you get to put everything, right? So it's in decreasing order of size of.
Yeah, I think that's I don't know whether it's strictly speaking optimal, but I think the heuristic that's using standard .typecons is just to order them in decreasing order of size.
Yep.
That's probably a reasonable approach. Walter?
It's not decreasing order of size of, it's decreasing order of align size of.
Right.
Okay, because like an array of bytes has no alignment, but you don't want to take the overall size of the array, you want to take the align size.
Yeah.
So.
But that's interesting. Maybe people could use that. For me personally, I like to say what my structure looks like, and I expect it to look like that. But I'm just old school or something. So the third one, and this is important, SIMD vectors do not interact with scalar types. Now people like to think they do, and it certainly seems natural to express scalar values with their scalar types. But this is a mistake. SIMD types only interact efficiently with other SIMD types. So people always come up with these like common linear algebra algorithms, like a dot product, which performs an operation on a vector that produces a scalar result. They'll write this little function which returns a float. It's the worst thing you can possibly do. Here we go, we have a float, scale 2, and a vector, v times a float. This is bad. This causes, though, D will syntactically accept this. The idea of supporting vector times scalar operations in D was so that you could perform a scale by a literal, but you can also syntactically perform a scale by a scalar. That requires a cast from a scalar value to a SIMD value, which is a slow, expensive process. And if you're writing SIMD code in the first place, you should be worried about that sort of thing. So don't do this. Instead, create a float 4 scale, which already does this. And you'll be much happier. If you do need to convert a float, let's say you have a float in a structure somewhere and you need to convert it to a scale, make sure it's not in your loop. Move it outside of your loops as far as possible. Another one that gets everyone, it's important to realize that individual elements are not randomly accessible. They must be digested in parallel. Everyone wants to do this. We have a vector, and we want to access the second element of the vector directly. Let's say set it to 0, lock a guy to the ground, or something as such. Array indexing syntax was removed from underscore underscore vectors for good reason. You cannot index, this is a compile error. So you need to perform all operations in parallel, effectively all operations in SIMD, and sometimes this requires getting quite creative. For instance, so here's a workaround. We want to set the y element to 0. We'll create a nice little scale vector here, which 1, 0, 1, 1, and then we'll multiply. This is the proper solution. That's one opcode, just a single multiply instead of a whole bunch more casts. And sometimes this does get really creative, trust me. If random access is absolutely required, then there is a .array property to get to the internal array, but you should only use this if you know exactly what you're doing. So, okay, that's a pretty good understanding of the general limitations. There's not too many more sort of critical ones. Question is, how can we put all of this to use without having to keep it in mind, make good use of the hardware without having to worry too much about these details? So I've been working on this library standard SIMD. I wanted to have a beta ready, but it'll be there soon. But I have a GitHub fork of Phobos, which people can check out if they're interested. The idea is to provide a complete set of higher level functions. So the SIMD functions are always targeting sort of very low level micro stuff. I provide like a full suite of functions. We'll see what they are in a sec. The idea is to map as efficiently as possible to the underlying architecture. The API is designed to encourage best practices at all costs. And I do try and fill in gaps in hardware support where an emulation can be performed efficiently on the architecture. But in the event that an efficient emulation of a missing operation is not possible, it will throw an error. So I'm just going to quickly skip over the sorts of functions that are available in standard.simd so you can all sort of just get a feel for it. So yep, there's the basic maths. The operators are available, but using these functions may increase portability slightly, because if there is an efficient emulation available for some type or some opcode that's not available on a particular architecture, these will fill the gap. There's standard set of bitwise operators. It's interesting to note these compounds, nor, and not. These can take advantage of a free complement on some architectures. You might ask, why doesn't the optimizer do this for me? The answer is it doesn't. It'd be nice if it did, but you really should just try and use these explicitly. You'll get the best results on the most possible architectures. There's some more compound functions. A fuse, multiply, add, subtract, negated multiply and add, and negated multiply, subtract. These are wildly powerful instructions. They'll double the speed of almost any sort of linear algebra code. You should use them at all costs. There's it's probably not right to use the term complex, but I'll call them complex maths. Sine, cos, power, they'll probably appear in the future, but I haven't written them yet. There's the standard suite of linear algebra functions, dot product, cross product, magnitude, normalize. There's also a bunch of fast estimates. These will attempt to be as fast as possible. Precision may or will be reduced, and the results may differ slightly between different architectures. So be careful. Usually I like to use these sort of not while processing data, but for high-level things, physics simulations, or rendering tasks where the result is a transient image rather than some important data that will get saved up. Andre?
Is there any support for sparse vector operations in SIMD?
Sparse, as in being able to take from.
They have a lot of zeros, for which reason they store them as interleaved index value. So.
Yeah, you can kind of.
I think I understood the answer.
I'll say no, but there's sort of opportunities. There are algorithms, but some of them aren't portable. Let's assume no. Let's go with that. Yeah, there's also a whole bunch of element permutation functions. These basically just swizzle around the elements in various different ways. Swizzle is, of course, a completely free swizzle, so it can actually replace all of these. And there's also an unaligned load, which you should use if you are performing unaligned loads, but as we'll see later, just don't. There's a comprehensive set of shifts, inter-element, within elements, whole vector, rotates and all that sort of stuff. We've also got type conversion. As we saw before, since SIMD types can store both floating point and integer data together in the same set of SIMD registers, it's possible to cast between float and int within a single register without, well, I'll get back to that anyway. And there's also data packing and unpacking functions. So there is a full suite of comparisons, and they can produce either bit masks, or you can perform Boolean any or logic. That is, if any elements meets a condition, or if all elements meet a condition for branching code. And there's also these branchless selection functions. They're really handy to minimize if statements and branches. Sorry. So you can get one of these bit masks, for instance, give it to a selection function, and it will select between A or B based on some predicate, and it will perform no branch in the process, which is good, and more. Right. Blah, 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 makes great effort to provide a uniform API, but if the target architecture can't perform an operation efficiently, it will produce a compile error. I think I've said all of these things, haven't I? Yes, I will comment again. Here's my comment that I thought existed. This is deliberate. I feel personally that it's much better that a programmer trying to make efficient use of SIMD know that they're performing an inefficient operation and have the opportunity to reconsider their approach. Maybe they can change their algorithm slightly, or do that part of the operation with a different type. So I don't want this to go away, and we'll probably make an effort to mitigate the GDC LDC problem in the future, but we'll see. Obviously, users may write a fully portable library above what D offers at its lower level, but they'll make compromises that they're comfortable with in terms of their product. So we want to get the best performance. Using these functions alone will not yield the best result. Implementing good SIMD code will often just result in a different bottleneck holding you up. Only by eliminating all of these bottlenecks will you truly unleash your code. Huzzah. So this may not strictly be SIMD related, but I wanted to go through some really common hazards that come up once people start using SIMD. The typical approach is that people will sort of get excited about SIMD stuff, they'll implement it, and then they'll go, my code's exactly the same. Doesn't run any faster. Might even be slower. It always happens. So you need to be aware of all other associated hazards, otherwise you won't really see any improvements. First one is always minimize your memory access. Memory is slow. Yes, particularly on embedded architectures. Treat it like the hard drive. You need to consider the allocation of your variables and registers. Make sure that there is enough registers available for the working data set. If there's not, then break it up into smaller pieces. You should preload variables outside loops wherever possible. So if you have like an expression that pulls data from a structure inside your loop, and for some reason the optimizer can't move that out of the loop on its own, you've got a problem. So I prefer to do that manually, make sure that any variables are loaded as far outside of my inner loops as possible. And never ever cast between register types. And this goes back to the whole float scalar thing. These casts almost always transfer via memory. Second important point, the ABI supports vector arguments when passing vectors to and from functions. Do use them. They'll be passed in registers. This will avoid stack access, thus more memory access. What I see all the time is that people are often in the habit of passing their sort of like non-SIMD vector classes, structures, whatever, and everyone has one of these. They're always passed by ref. And through force of habit, they sort of translate this to SIMD, and that's the biggest mistake. 3, so use leaf functions wherever you can. So what's a leaf function? These are functions that have no reason to allocate a stack frame at all. thus eliminating more memory access again. If we can avoid allocating a stack frame at all, then we know we're not going to be using it. There's a whole bunch of criteria to qualify your function as a leaf function. The first, it can't call any sub-functions unless they're small enough to be inlined. So it can't receive any non-primitive arguments that would usually pass on the stack. It may not return a structure by value that would usually return on the stack. Actually, name return values might actually improve this. It might be possible to do that. Tentative, try it out. And don't cast between register types. Otherwise, it'll use the stack. Also, you need to, again, worry about the number of locals you have. Make sure that, that there's few enough locals that you have registers, and if there isn't, then break it into two separate functions, if possible. This usually always results in good gains, especially within hot loops. If you've got a tight loop running over some function, and you really don't want to sort of just inline all of that code and just have this massive blob of stuff in your loop, make sure all the functions that it calls into are leafs, and you'll see basically the same results as if you just pasted your code straight in line. Number 4, only cast SIMD types. So it is possible to cast into float, but you need to do it within SIMD registers. Never take an integer or a float and cast it to SIMD for reasons I've already discussed 2 or 3 times. It's very nice that SIMD registers can hold types of, or can hold values of all different types. So, you know, use that to your advantage wherever you can. Avoid unlined loads, like really, just don't do it. It's a really slow process. It looks like this. So here's a typical looking vertex stream, something that I'm very familiar with. So this vertex is not aligned to 16 bytes, although I wouldn't have made this mistake under normal circumstances. We want to load the position of our second vertex, but it's not on a 16-byte boundary. So what the CPU has to do is chop off the bottom 4 bits of the address that we're trying to load, and then it will load the first vector and the second vector into 2 separate registers. So we've now doubled the number of loads. Now it's got to shift both of these vectors into the appropriate places, and then it ORs them together. That's like 5 times as much work, and they're all dependent on each other. Just don't do it. Now, this is starting to get pretty low level, but I'll talk about it anyway, because this is where almost all algorithms get stuck. You need to pay pretty careful attention to your pipelining. The SIMD operations do tend to have a high latency, often enough slightly higher latency than the scalar operations. As a result, if your operations are heavily dependent on the results of the previous one, you may see slower performance using SIMD than if you used just scalars directly. You can unroll your, if you can't break the dependencies, then you can unroll your loops a little bit, and maybe we could use a system like David described earlier, actually. Of course, if you can break up your dependencies, you should. So this might not be the best example, but unless you turn fast math on, and assuming these are floats, this x plus y plus z plus w must be performed in sequence, and the compiler will not rearrange it because of IE precision reasons. So you end up with something that looks like this. The first add, the second add begins when the first add completes, and the third add, and all of these lines in between are wasted CPU cycles. So the CPU can usually issue 2 or more opcodes per cycle. But it's not doing anything here. It's really just waiting for the previous opcode to complete before it can issue the next one. This is really trivial. If you simply put brackets around here, then we can kick off x plus y and z plus w effectively in parallel, and then add them together, and we've gained big. Now, this will come up all the time, and not necessarily with addition, but with more complex operations. So you need to just try and get as much overlap as possible. Yeah.
Is this SIMD specific or in any?
This is certainly
Repeat.
in any code, but
Repeat question.
sorry. The question is this SIMD specific or any types? And I'll say this: any code applies this principle, but the point I made before was that SIMD operations often have a slightly longer latency than their scalar operations. So if you're not conscious of this and you apply SIMD, you might see slower performance unless you're aware of this kind of behavior.
There's a cost to that behavior. It costs you another register, which if it then causes you to spill, you're worse off.
Certainly true.
So that with most optimizations, there's always a pessimization possibility with it.
In x86, where there's only 8 registers, then that's a pretty important consideration. In x64 now, there's 16 registers. If you're using AVX, then there's 3 operands. So that's a long story. So x64 is nowhere near as likely to spill registers as x86. And both PowerPC and ARM and MIPS and anything else I've worked with have bunches of registers comparatively. I rarely find myself running out of registers, except for on x86, and x86 is the single architecture that can tolerate it the best. So, but still, yeah, it's important to keep this in mind. But we're in a land of real micro-optimizing here. But yeah, you should try and strive for this at all costs. And if you can't restructure your code to look more like this within your loop, then you should consider unrolling your loop a little to try and get sort of a couple of processes of this happening side by side. And they'll fill in the gaps just by unrolling it. 7, bandwidth. Was there a question? No. So, yeah, aggressively optimized code, in my experience, will almost always become bandwidth limited. That's a pretty good place to be in if you've become bandwidth limited. Here's some tips. So, firstly, you do want to pack your data where possible. There's a bunch of unpacking functions in the SIMD API. If you can fit your data into smaller types, then do it and unpack them as the first step of your algorithm. It's almost always faster than fetching from memory. And make sure that your data is packed into 16-byte blocks because we need to do align loads. And if you're not in 16-byte blocks, you're wasting a few bytes of padding. So keep that in mind. You should always be aware of the decache. Access your memory linearly if possible. And if you are randomly accessing, then try and at least keep it localized. Use pools for allocating rather than just random scattered heap allocations. And D's garbage collector actually helps with this a lot because the garbage collector allocator uses pools naturally. If you're crazy enough, you can experiment with prefetching. I'm crazy like that. So, as a little recap, what have we learned? I maintain you must test every architecture explicitly. If you don't, fall back to some standard D code until you can test it. You should pay careful attention to data alignment at all times. Avoid accessing individual elements. Try and perform all operations in parallel always. Just don't cast. Do use compound operations. They're a massive win. Avoid memory. Think of it like the hard drive. I took this slide out. Ifs bad as well. You don't want unpredictable ifs. Unpredictable ifs are almost as bad as fetching memory, so I had a slide, but I took it out. I was going to talk about the select thing, but I talked about that briefly. But if you do have ifs in your loops, make sure they are predictable. If you have an unpredictable if, then try and use the select function that I said before, where it will select between the result A and B based on some predicate. It's often faster to calculate both A and B in parallel and then select between them based on a predicate than it is to perform an if and then perform one calculation or the other. Did you have a question?
Well, yeah, with regard to unpredictable ifs, there's been this, just a note, there's been this thread making the rounds on Stack Overflow on summing all elements of an array, and it was like, 5 times slower if the array was random, contained random numbers. Sorry, it didn't sum all elements, it summed all positive elements in an array.
Oh, okay.
And if the numbers were random, the test would be completely unpredictable, so it would mess up the... Whereas if it were sorted, it would be like so much faster.
Brilliant faster. The branch predictor is probably more important now than ever as architectures get faster and pipelines tend to get longer, or there was a little period where they were getting shorter. The predictability of ifs is a very big facet of CPU's performance. If your if is just naturally unpredictable, then there's not much it can do to help you. Jonathan?
Maybe I'm just clueless, but what is an predictable if versus unpredictable if? What's being predicted?
Well, the result of the comparisons. So you have some condition that causes it to branch A or B. The result of this comparison, if it always goes A, or at least almost always goes A, then you'll get much better performance than if it goes A then B sometimes. And actually, the CPUs are okay at understanding if it goes A B all the time. So even if it's got a really good concise pattern, some CPUs can deal with that as well. But if it's just quite random, and it might be if you're dealing with SIMD code, you're probably dealing with, like I say, image processing or physics or vector processing. You know, this is random data just coming in. You'll never get good predictability out of it. So it's just a good rule of, a good habit to eliminate the ifs and use selects instead. And of course, pay attention to your pipeline, unroll your loops, and try and perform concurrent operations where possible. Yes, questions? I'm sorry, that was... Hello, Walter.
Yes, on the regular ALU, it has separate integer and floating point parts. So if you structure your code properly, you can run your floating point ops and your integer ops in parallel.
Absolutely.
Now, the SIMD operations support both integer and floating point operations. Is there a similar scheme where there's a SIMD floating point unit and a SIMD integer unit that can run in parallel?
I've never heard of an architecture like that. But you're typically going to be using your integer hardware still for processing like loop counters and that sort of logic. So as long as your integers stay isolated, you'll get them for free. If you're doing int work and you're doing SIMD work in the same loop, they'll run nicely in parallel, and neither will, you know.
Okay, so...
But I've never heard of a SIMD architecture which splits it that way.
Okay, so does that also mean you can potentially have your integer operations, your floating point operations, and your SIMD operations all running in parallel?
You certainly can.
Okay.
But it depends slightly on the architecture. Like some CPUs will have sort of different processing units. It'll be dispatched to a different area on the processor. But most of them do have totally isolated sections for int, float, and SIMD. But some do sort of conflate float and SIMD. For instance, x64 ABI now doesn't. They've deprecated the x87. And this is important, actually. x64 is the most tolerant SIMD processor in the world. And as such, I don't recommend using x64 to judge performance of your SIMD code performance. That was redundant. Don't test on x64 if you can avoid it, because it will always show the best results. And the reason for that is because the x87 is deprecated. It uses the SIMD registers now for doing all floating point operations. So, funnily enough, on the x64 and only on the x64, it is fast and efficient to cast between float and SIMD. But that doesn't mean you should do it, because you'll be wiping out the portability of your library. Yeah.
I wondered to what extent you can infer automatically vectorization using SIMD in DMD code, because whenever you're doing it in your source code, it invariably becomes uglier, and also it depends on architectural support. Whereas compiler could be actually, has enough scope to infer like for loops, so it could do a better job at it.
Well, it's possible. There's a few key issues, though. The first is that, sorry, without actually using something like __ vector, the compiler can't assume that any data is aligned. So you'll almost always be performing unaligned loads and stores if you want auto vectorization from the hardware. And an unaligned store is even worse than the unaligned load that I demonstrated. LDC and GDC will both do a pretty good job of auto vectorizing where they can, but DMD doesn't try at all. It's a really hard problem to even address, so I don't imagine DMD trying to do it anytime soon. I think you should just try and work with the libraries.
The front end could have more information than the back end to do it.
The front end, you say? Sorry, the front end could have...
Yeah, the front end might have more information than the back end. Maybe if it's at the level of the LLVM optimization, it's a little bit too late to do those things.
Does it, though? Maybe. Yeah, I guess. If you were to declare like local short arrays without underscore vector, and the front end thought, well, maybe I'll just align this one, then maybe. But it's, I don't really see any disadvantage to using a SIMD type there. Like I say, it's only going to make the most difference. You're only going to go to all of that effort in really hot code, I think. So, anywhere else, that sort of attention to to code performance isn't likely to be worthwhile your time.
So you had mentioned prefetching. I actually discovered recently that that's a really efficient way, on a slightly unrelated note, to speed up tree traversals, is to, if you don't know whether you're going left or right, prefetch both before you execute the unpredictable branch to determine whether you're going left and right. Are we getting prefetch intrinsics in standard.simd or standard.intrinsics anytime?
There's prefetch intrinsics available right now in LDC and GDC.
But I want portable.
Yeah, I don't know if there is one available in DMD. And once we have them in all compilers, then it's easy to write an API in either standard.simd or somewhere else that combines them. So my answer is no, but I'd like to see it too.
I guess I should make a comment about auto-vectorizing. I read a book on how to auto-vectorize compilers, and one of the huge problems with auto-vectorizing is the average and even the expert programmer cannot look at a loop and tell if it auto-vectorized successfully or not, because it depends on all kinds of weird and unusual things, whether it can do the auto-vectorization or not. So this leads you to the point where your code can suddenly become slow and you don't know why. So Dee's approach, I think, should be to not auto-vectorize. You should specify SIMD and vector loops at a higher level, and then you will know if it's auto-vectorizing or not without having to dump the assembly code and look at it.
But for what percentage of code do you actually care? I mean, what is it, 99% of code takes up 1% of your CPU, so if you auto-vectorize most of that, nobody will notice, but...
SIMD is for people who care.
Well, I'm thinking
Frankly, they care about it, the people who use SIMD. They want to know that it auto-vectorized and it auto-vectorized, and they're getting the performance that that is advertised by the CPU. And an auto-vectorizer that sometimes randomly to them doesn't auto-vectorize is a time waster for the programmer.
Yeah, but if you're in that 1% that really matters, yeah, of course, use the explicit SIMD, but what about, could we get benefits in the rest of the code as well? Okay, we make it a little bit faster.
Yeah, maybe, but maybe not, and you can't really be sure. I might add too that chances are you're not going to be using SIMD directly. You're going to be using a library that's using SIMD directly, and that library author might think it's worthwhile going to the effort of doing this to provide their library, which then everyone will benefit from. So, I'd rather see a good set of explicit functions which will make noise and warn you when you're doing dangerous stuff or doing things that won't port well, than to just try and do it everywhere. It's better that the library is able to deliver a predictably, reliably good result. Ooh. That's all right. Anyone else? So, might add one further thing. I was going to put a case study sort of showing the effects of all of these things on a nice case study progressively in this talk, but I didn't get sort of time to manufacture it. I will still do that, and I'll put it on the website where these are published along with it so people can actually see the effects those points have on real code.
By the way, we'll put slides for the all talks soon on the conference website for each on each talk page. So I encourage all speakers to do minute changes to their slides. Fix that last typo, put the last comma. Don't forget, commas are important. And thanks, Manu. Let's take like 10 minutes break.